In that last example, we just used properties of logarithms just to make finding the derivative a little bit easier. This is the idea behind another process called logarithmic differentiation. And that is a method that involves using implicit differentiation and properties of logs when we take a derivative. So we can use logarithmic differentiation even when we don't see a logarithm appearing in a function. So for example, this function doesn't have a logarithm appearing in it. But one method of finding the derivative of this function would be to take the log of both sides and use those log properties and implicit differentiation and then solving for y prime. So here's an example. So to find the derivative of this, I take the log of both sides, and then now that I've done that, I have a log of a product, and I can use that property of logarithm that splits it up into splits it up into a sum, and then I can bring down that power on the argument to the logarithm. That also is another property of logarithms you need to remember. And so now we can differentiate term by term. So we differentiate on the left using, so this is the part where we use implicit differentiation. So the derivative of ln of y is simply y prime over y. So the 1 over y, the y in the denominator comes from the derivative of the logarithm, and the y prime comes from the derivative of the inside. We're treating that y as a generic function. And then we take the derivative of this side. So notice that ln is an outside function. So the derivative of this term is going to turn into my function is, the inside function is going to be in the denominator, and then the derivative of the inside function will be in the numerator. And I'm just multiplying it by 2, so that numerator is 4x. And I do the same thing here. So now notice that I still have a y here. So I solve for y prime by multiplying both sides by y. And what is this y? It was just the original function. So I just replace this y with the original function. And that's it. So you can make the argument that this actually would have been easier to differentiate with the product rule, but I just wanted to illustrate where you can use logarithmic differentiation in functions that you've found the derivative of before. So there are functions though where we don't know how to differentiate, and we need to use logarithmic differentiation. And one case is where there's a function of x and a power of x. So for example, I have the square root of x raised to the x power. So we don't know any techniques that help us find the derivative of that. That's not an exponential function because the base is not a constant. It's not a power function because the power is not a constant. So this is something that we don't know how to differentiate, but now we can do it with logarithmic differentiation. So I am going to take the logarithm of both sides. It doesn't really matter which log I take, what base log. I'm going to use ln because that's the easiest, because I don't have to remember that extra factor. So I take the log of both sides. And then the reason this is so handy is if you use that power rule from logarithms, where you can take the exponent of the argument to the log and bring it outside the logarithm, like this. So now I'm going to use implicit differentiation and differentiate term by term. So the derivative of the ln of f of x, since the ln's the outside function here, is just f prime of x over f of x. And then I'm going to use the product rule here, and that simplifies to the ln of square root of x plus 1/2. So now I need to solve for just f prime of x. So I'm going to multiply this by f of x. And what was f of x? My original function was the square root of x raised to the x. So in summary, you're going to want to familiarize yourself with these three forms here. The derivative of the ln of a function and the derivative of log base b of a function. That's when the logarithm's on the outside function. Otherwise, you just use the chain rule as normal. And remember that the properties of logs can make differentiation easier if you remember the properties. And logarithmic differentiation is sometimes required with certain functions, especially when you have a function of x raised to a function that also contains x.